I want to show you still another way how to solve a system of linear differential equations. Z derivative is a matrix A times the vector Z. If we know the eigenvalues and eigenvectors of the matrix, say A V1 is lambda 1 V2, lambda 1 V1, and A V2 is lambda 2 V2. There may be even more of them, but for the moment let's assume that the eigenvalues are different. Then we can build a matrix V with the columns being the eigenvectors. And we can build a matrix lambda, which is diagonal, and on the main diagonal we have the eigenvalues lambda 1, 0, 0, lambda 2. Then these two lines can be written in a single line. If we write A times V, that means we copy the matrix A and then we multiply by V1, the first column of V, and then after that we just copy V2, the second column of V. And we want to write this is equal to the same columns, V1 and V2, but the individual columns should be multiplied by two individual values. Multiplying a matrix in such a way that individual columns are multiplied by some numbers can be done by multiplying by the diagonal matrix. We must be careful whether we multiply from the left or from the right. Let me explain this in an extra part here. Say if we have the matrix ABCD, and let's assume we multiply with the diagonal matrix 2, 3 from the right. Or we take the matrix ABCD and we multiply by the same diagonal matrix from the left. Let's see what happens. In this case we have 2A plus 0, 3B. And here we have 2C plus 0, 3D. So we multiply individual columns with these values. If we multiply the same matrix with the same diagonal matrix, but this time from the left, the result is 2A plus 0, 2B plus 0, 3C, and 3D. This time we multiply individual rows with these numbers. But we want to multiply the columns. So this is what we want. We want to multiply the matrix by the diagonal matrix from the right. So this is the matrix with the columns, with the eigenvectors, and we multiply from the right by the diagonal matrix lambda, having the eigenvalues on the main diagonal. Well, and if we multiply by V inverse from the left, then here we have A, V inverse, but V times V inverse is the identity matrix, and multiplying by identity matrix means leaving the A alone. And on the right we have V, lambda, V inverse. This is a useful decomposition of the matrix A, because if we use it into the differential equation, we have Z derivative is V, lambda, V inverse, Z. And now if we multiply by V inverse from the left, we have V inverse Z derivative is equal to lambda V inverse Z. And now substitution can be used, namely V inverse Z for some vector, say W, and then this is the derivative of W. And using this substitution, we can transform the original system of differential equations into a system of differential equations where the matrix is diagonal. That means it splits into individual independent differential equations. Namely, the first component is lambda 1 v1, and the second component, derivative, is lambda 2 v2. We can solve this. v1 is v2 lambda 1t v1 at 0. We can solve this. e2 lambda 2t times v2 at 0. This is at t. And we are done. So, having any initial condition, we write the initial condition in terms of w. We have these values, and having the eigenvalues, we have the solution at any time t in terms of w, and then z is equal to v w. So, well, this is not easier. We have to find the eigenvalues and eigenvectors, but this is just another form of writing the results, another form of expressing the results, which is quite a useful conception. We can rewrite the same idea even in the form of z at time t being exponential of a matrix times z at 0. Isn't it nice? If A is just one number, 1 by 1 matrix, this is just the result that we have seen at the beginning of this chapter. And this works even for matrices. Perhaps we should explain what we mean by exponential of a matrix. First, if A is 2 by 2 matrix, then multiplying by a scalar t is again a matrix. And exponential of a matrix, if we go back to exponential of a real number, then this can be written as 1 plus x squared half plus x cubed over 3 factorial plus x to 4 over 4 factorial and so on. In general, this can be written as sum of x to n divided by n factorial, n running from 0 to infinity. This works not just for real numbers x, this works perfectly well even for complex numbers, and this works even for square matrices. Because if x is a square matrix, we can compute a by a times a times a times a, any powers, any positive integer powers of the matrix are possible, and we can divide by a real number. So e to a is, instead of 1, we have the identity matrix, and then we go on plus a squared, which is a times a divided by 2, plus a2, which is a times a divided by 3 factorial plus a to 4 divided by 4 factorial, and so on. So this is still another nice, short, compact, elegant way how to write the solution. It does not help in the sense that we have no more computation or easier computation, we still need eigenvalues and eigennumbers to compute the exponential. But this is a quite useful way how to write the result.